This video is on the modulus function. So the modulus function takes any number and makes it positive. So for example, let's say that we had -5. If we took the modulus of this basically means that we put these two straight lines here, and the modulus of -5 would just be 5. It makes it positive and it gets rid of the negative symbol. If we did the modulus of -3 over 4, again we do this by putting these two straight lines here, this would be equal to 3 over 4. It gets rid of this negative sign here. And if we took the modulus of 2, this would just be equal to 2. There's no effect because 2 is already positive. If we had a function f of x and we said that f of x is equal to the modulus of x minus 10 minus 1, if we did f of 1, this would be equal to the modulus of 1 minus 10 minus 1, which would be equal to the modulus of -9 minus 1, and then -9 becomes +9 minus 1, and this would just be equal to 8. If we did f of 12, it would be equal to the modulus of 12 minus 10 minus 1, which would be equal to the modulus of 2 minus 1, and then the modulus of 2 is just 2 still, because this is already positive, and then it's 2 minus 1, and this is just equal to 1. So the modulus basically works as a pair of brackets. You have to do whatever is in the modulus first. So what does the graph of a modulus look like? Well, here we have the graph of y is equal to x, and if you apply the modulus to a graph, it will reflect everything in the x-axis when y is less than 0. So the graph of y is equal to the modulus of x will look like, well, this part would be normal because this is above the x-axis and it's positive, so this would just be the same graph. But here the graph is below the x-axis. The graph is negative, so therefore this will become reflected in the x-axis, so this would look like this here, where the red is the graph of y is equal to the modulus of x. And if you think about it, this makes sense. Here the modulus has no effect at all because all the values are positive. So for example, here where x is equal to 1, the modulus of 1 is still equal to 1. But for here, for example, here x is equal to -1 and the modulus of -1 is equal to 1. Now normally for y is equal to x, y would be equal to -1 as well, but the modulus makes it equal to 1, so it becomes up here. And this is the case for all the values. So it's a reflection in the x-axis. So here's an example question where we need to sketch the graph of y is equal to the modulus of 2x plus 5. Now for questions like this, as I've kind of shown in grey, I would always first draw the normal graph, kind of like a the non-modulus graph, kind of like as a rough working. So here I've done this as y is equal to 2x plus 5, and this is quite a good thing to base your answer off. And this here has a y-intercept at 5, and it has a root at -5 over 2. Okay, so let's sketch now y is equal to 2, the modulus of 2x plus 5. So this part here is fine because this is above the x-axis, so this here will remain the same, but this here is below the x-axis, and now this will get mirrored in the x-axis because it's negative, and this will come up like this here. And this is the graph of y is equal to the modulus of 2x plus 5. Note that the y-intercept and the root haven't changed because they're part of this original line here. So here's one more very quick example. We need to sketch the graph of y is equal to the modulus of -1/2 x minus 2. So firstly, sketch the graph of the graph without the modulus. So this is -1/2 x minus 2. So I do this not on camera because it's really hard to draw straight lines on a drawing tablet, but this is the graph here where the y-intercept is going to be -2 and the root here is going to be -4. And now we can sketch the graph of y is equal to the modulus of -1/2 x minus 2. This here is fine because this is still above the x-axis, so this here is going to be the same, but this here is negative and below the x-axis, so we're going to mirror this in the x-axis, so this is going to come up like this here. And this is going to be the graph y is equal to the modulus of -1/2 x minus 2. The root is going to be the same. This is still going to be minus 4. And this y-intercept here is changed. It's no longer down here, it's up here. But because it's a reflection in the x-axis, this is just going to be positive 2. It's a modulus, so this point here, the y-coordinate is minus 2, but because of the modulus, it becomes positive 2, like this. Now, you may be asked to solve equations involving moduluses. So here's an example where we need to solve the equation the modulus of 3x minus 6 is equal to 15. So if you recall back to the simultaneous equations and graphs video, when we say that these two things are equal to each other, another way of saying this is when the graphs y is equal to the modulus of 3x minus 6 and the graph of y is equal to 15 have points of intersection. And to solve questions like these, especially with moduluses, it's really important to draw a graph. So let's do this. So firstly, let's do a rough sketch of y is equal to the modulus of 3x minus 6. And to do this, let's first sketch the normal graph, y is equal to 3x minus 6 without the modulus, which will have a y-intercept at minus 6, a positive gradient, and a root at 2. So this is the graph of y is equal to 3x minus 6. And then to sketch the graph of the modulus of 3x minus 6, we have to reflect everything that is under the x-axis in the x-axis. So this part here is fine because this is above the x-axis, so this is going to remain the same. And then this here is below the x-axis, so therefore this is going to be reflected in the x-axis, so this is going to look like this. And this graph is equal to y is equal to the modulus of 3x minus 6 here, where the new y-intercept here is equal to 6. So that's the graph of the modulus. So now we need to sketch the graph of y is equal to 15, which will just be a straight horizontal line when y is equal to 15. So it will look something like this. Sorry for the cut, so it's really hard to draw straight lines on a drawing tablet. So we can now see that there are two points of intersection, one here and one here, between these two graphs. And this is why it's important to sketch a graph to see how many points of intersection there are, as it will not always be 2, as we'll see in a sec for the upcoming questions. So how do we solve this? How do we find these 2 points of intersection? Well, the reason there's 2 points of intersection is because of the modulus, and because when this expression inside the modulus is positive and when it is negative, usually this will equal 2 different things, 15 and minus 15. But because of the modulus, this is no longer the case. They both equal 15. And we can use this to solve the equation. So let's do this. Okay, firstly, let's consider when this expression inside the modulus is positive. So this will be 3x minus 6. This is the positive expression. And this is equal to 15. Move the minus 6 onto the other side to get 3x is equal to 21, and then divide both sides by 3 to get x is equal to 7. And this is one of the solutions, x is equal to 7. Okay, now let's consider when this expression inside the modulus is negative, because obviously normally when this is negative it will equal minus 15, but because we have this modulus it will equal 15 instead. So let's consider when this expression is negative, so this is going to be minus of the expression 3x minus 6, and this is equal to 15. Expand the brackets to get minus 3x plus 6 is equal to 15, so minus 3x is equal to 9, and divide both sides by minus 3 to get x is equal to minus 3. And these are the two solutions, when x is equal to 7 and when x is equal to minus 3. So the actual technical reason this works is because we are actually considering two different lines. When we're considering this expression as positive, as we did here, we are considering when the lines y is equal to 3x minus 6, the positive expression, and the line y is equal to 15 when these two lines intersect. And this is going to be, so this is the line y is equal to 15, and the line y is equal to 3x minus 6 is this line here. So this point of intersection here is going to be the x is equal to 7. And when we're considering this expression to be negative, like we're doing in this part here in purple, we are actually considering when the lines y is equal to minus 3x plus 6, the minus, the negative of the expression inside the modulus, and the line y is equal to 15 intersect. So this is the line y is equal to 15, and the line y is equal to minus 3x plus 6 is actually this section of the line here. You might actually be able to see it quicker, if easier, if we expand the line like this fully, that this is the line y is equal to minus 3x plus 6. So therefore we have 2 points of intersection. One when this expression is positive, and this is this point of intersection here, and the other when this expression is negative, and this is this point of intersection here. So here's another example, this time with a function of x equaling the modulus instead of a constant like last time. So this is the same thing as before. When we say that these two things are equal to each other, another way of saying this is where the point of intersection is between the graphs y is equal to the modulus of 3 over 2x plus 7 this side, and the graph y is equal to a half x plus 10. So we need to sketch both these graphs and then see how many points of intersection there are. So first of all, let's sketch the modulus of 3 over 2x plus 7, and then first of all let's sketch 3 over 2x plus 7. So this is the graph of 3 over 2x plus 7, where the y-intercept is 7 and this root here is minus 14 over 3, and then the graph of the modulus of 3 over 2x plus 7 is going to be anything that's under the x-axis is reflected. So this part is fine because it's above the x-axis, so this is going to be the same here, and then this is under the x-axis, so this is going to be reflected, and it's going to be like that, where this is y is equal to the modulus of 3 over 2x plus 7. And now we need to sketch the graph of half x plus 10. And then this is the graph of y is equal to a half x plus 10, where the y-intercept is 10 and the root is minus 20. Now, a good sketch is really important, and when the two functions are equal to each other, when two functions of x are equal to each other, the gradients are really important as well, and the y-intercept. So this gradient is greater than this gradient, so therefore this line is steeper than this line, and this y-intercept is greater than this y-intercept, so it's higher up. And because of this, this allows us to see for our sketch that there are 2 points of intersection. In the next question, we will see an example where there are not 2 points of intersection, and the way that we see that is again by drawing an accurate sketch of the gradients and the y-intercepts of the line. So this is important. The only way that we can see that there are 2 points of intersection is because we draw it accurately, with this gradient being greater than this gradient. So that's quite important. Okay, now let's actually solve the equation. So first of all, let's consider when this is positive. So this is going to be equal to when 3 over 2x plus 7 is equal to a half x plus 10. I'm going to move the 7 onto the other side to do 3 over 2x is equal to a half x, and it's going to be plus 3, and then move the half x onto the other side to do x is equal to 3. So that's one of the solutions, and then the other solution is when this is a negative expression. So this is when it's minus 3 over 2x plus 7 is equal to a half x plus 10. Expand the brackets to get minus 3 over 2x plus, or minus 7, sorry, is equal to half x plus 10, and then move the minus 7 onto the other side to get minus 3 over 2x is equal to a half x plus 17, and then move the half x onto the other side to get minus 2x is equal to 17, so therefore x is equal to minus 17 over 2. And these are the two solutions, when x is equal to 3 and when x is equal to minus 17 over 2. This is going to be the x is equal to 3 solution, and this is going to be the x is equal to minus 17 over 2 solution, because as we talked about before, this is the negative expression and this is sort of the negative line, and this is the positive expression and this is the positive line. So here's another example. So we have this modulus is equal to this equation. So again, this is when, another way of saying this is when the graphs y is equal to the modulus of x minus 2 and the graph y is equal to 4x plus 7 have their points of intersection. So the first thing that we need to do, as always, is sketch a graph. And the first thing we're going to do is just do the x minus 2 without the modulus. So this is the graph of x minus 2 where we have a root at 2 and the y-intercept at minus 2. And then the graph of the modulus of x minus 2 is, so this part is okay because it's on top of the x-axis, so this is going to be like this. And then this is below the x-axis, so this is going to be mirrored, so this is going to look something like that. And this is the graph y is equal to the modulus of x minus 2, and this here, the y-intercept here, is going to be 2 because it's mirrored here. This is minus 2, so this is going to be positive 2. And now we need to sketch the graph of 4x plus 7. And then this is the graph of y is equal to 4x plus 7, where 7 is the y-intercept and the root is minus 7 over 4. And you can see that there is only one point of intersection. And this is the power of an accurate sketch, because we can only see that there is one point of intersection because of our accurate sketch. We've done the gradients in proportional to each other. This gradient is 4 and this gradient is 1, because remember the coefficient of x is 1. And we have done that this line is steeper than this line and has got a greater gradient. We've also done this with the y-intercepts as well, that 7 is greater than 2. And because of this accurate sketch, we can see that in this case there is only one point of intersection. If we just did this rough and we said that, okay, the modulus looks something like this and the line looks something like this, we might think that there are 2 points of intersection. But because we've done this accurately with the correct gradients and y-intercepts, we can see that there is only one point of intersection in this case. So the question is now, mathematically, how is there only one point of intersection? And which one is it? Is it when this expression in the modulus is positive, or is it when it is negative? Well, let's go back to what we talked about before about which line is which. This here is when the expression is positive, because this is the line of x minus 2. And then this line is when the expression here is negative, because this is the line of 2 minus x. And you can see that the point of intersection occurs here when this line is the negative expression, when it is 2 minus x. That's where the point of intersection is. So therefore the point of intersection and the solution is going to be when this expression is negative. And again, this is the importance of a good sketch, because the only reason that you can see this is because we have done the gradients correctly, and you can see that it is this line here when the expression is negative. So let's do this. So this expression is negative, so it's going to be minus of x minus 2 is equal to 4x plus 7. Expand the brackets here to get minus x plus 2 is equal to 4x plus 7. Move the plus 2 onto the other side to get minus x is equal to 4x plus 5. And then move the 4x onto the other side to get minus 5x is equal to 5. And divide both sides by minus 5 to get x is equal to minus 1. And this is the solution. X is equal to minus 1 for this point of intersection. Now, just out of interest, you might be wondering what would happen if you did solve as well with this expression being positive. And you would get an answer. If you did the maths, you'd get an answer of x is equal to minus 3. And just when you look at it, this is like a reasonable answer. However, when you look at the graph, you can see that minus 3 is about here. But this line here does not go up to minus 3. This is minus 3, but this only goes up to 2. Minus 3 does not lie in the region of this section of the line here. So therefore, it is not a valid solution. If you extended this line like this, remember this is the line of x minus 2, the solution is down here when x is equal to minus 3. And this is what actually this is saying. That x is equal to minus 3 is a valid solution for x minus 2, but it is not a valid solution for the modulus of x minus 2, because the line here doesn't go up to minus 3. It doesn't go that far. Another way you could check your answer to see if it's correct is if you sub them into this line. So if you sub minus 1 into this line, you get that it's 4 of minus 1 plus 7, which is equal to minus 4 plus 7, which is equal to 3. And if you sub in minus 3 into this line, you get, so it's 4 of minus 3 plus 7, which is equal to minus 12 plus 7, which is equal to minus 5. 3 is bigger than 0, but minus 5 is less than 0. So 3 is fine as a solution because the modulus here can equal 3 because it's positive, so therefore the modulus can equal it. But minus 5 is not a valid solution because the modulus cannot equal a negative number. Obviously the modulus is always bigger than 0. So therefore we have one point of intersection because this line doesn't go far enough in order for x minus 3 to be a solution. They could also ask you an inequality question if there are 2 points of intersection. So here's an example of this, and this example is actually specifically mentioned on the spec. So we talked about this in the inequalities on graphs video in a bit more detail. But basically the way that we'd want to approach this is we would want to draw the graph first, like we've been doing with all the other ones. So again, we want to draw the graph with the graphs y is equal to the modulus of 2x minus 1, which is one side of the inequality, and the other one would be y is equal to x. So let's sketch this, and let's first start with the modulus. So the first thing we want to do is sketch the graph 2x minus 1. So this is the sketch of 2x minus 1, where we have the root here as half and we have the y-intercept as minus 1. And then the sketch of the modulus of 2x minus 1. So this here is fine because this is on top of the x-axis, so this is going to be like this. And then this here is under the x-axis, so therefore this is going to be reflected in the x-axis, so it's going to be like this here, where this is the graph, y is equal to the modulus of 2x minus 1, where this now is going to be the y-intercept of 1, because this is reflected up here. And all we just need to do now is sketch the y is equal to x graph, and this is the line y is equal to x, and if you draw it accurately enough, you can see that there are 2 points of intersection. Now refer back to the inequalities on graph video again if you need a bit more detail on this, but the way we would solve this inequality from here is find these 2 points of intersection, and this can be used in order to solve this inequality. I'll show you how to do it. So first of all, let's find these 2 points of intersection. This is the same thing that we did before. Firstly, let's do it when this expression is positive, so this is going to be 2x minus 1 is equal to x. Again, we're using the equal sign because we want to find these points of intersection. First, move the 2x onto the other side, or I'll move the x onto the other side actually to get x minus 1 is equal to 0. So then x is equal to 1, and this is one of the solutions. You'll find that this is actually this solution here because this is the 2x minus 1 line, so this is the positive expression solution. And then the other solution is going to be when this expression is negative, so it's going to be minus 2x minus 1 is equal to x, expand the brackets, do minus 2x plus 1 is equal to x, move the minus 2x onto the other side to get that 1 is equal to 3x, and divide both sides by 3 to get that x is equal to 1 over 3. And that's the other solution, and this is going to be this one here. So this solution here is going to be 1, and this solution here is going to be 1 over 3. Now we need to find the set of values that satisfy that the modulus 2x minus 1 is bigger than x. So this is the y is equal to x here, and this is the modulus y is equal to the 2x minus 1, and we need to find when this is bigger than this, and this is here, this is bigger, and here this is bigger. This is the only section where it's not the case, because you can see that the y is equal to x line is on top of the modulus. So this is the only section here, and this is between the points of intersection, and we know the points of intersection. We know it's 1 over 3 and 1. So therefore what we can do, we can say that this is only the case 2x minus 1 is bigger than x when it is less than 1 over 3 this way, so less than 1 over 3, so when x is less than 1 over 3, or over here where x is more than 1. This is the only case where it's not the case. So when x is less than 1 over 3 here, and when x is more than 1 here, that is when this is bigger than this. And that's the final answer. So this is all I'm going to cover for this video on solving modulus equations, as I'm going to make an entire video dedicated to solving modulus problems in this chapter, like the book does by making a chapter solely on it. And they're very common exam questions that they ask a lot. So now let's move on to graph transformations. So if we have the function f of x, the graph transformation, the modulus of f of x, will reflect where f of x is less than 0, so this is when it's below the x-axis, it will reflect it in the x-axis. So we've seen this already with the straight line examples. I'm just going to do one more example to kind of aid this explanation. So this part here is fine because it's on top of the x-axis, so this is unaffected. But this is below the x-axis, so this is going to be mirrored in the x-axis, so it's going to be like this, where this is y is equal to the modulus of f of x. The root and the y-intercept in this case stay the same, and as we talked about before, this makes sense. If this point here is -1, the only effect is it now becomes the modulus of -1, which is just equal to 1. So it's the exact same position, it just becomes positive now instead. They could ask this for any graph, so they could ask it for a quadratic, for example. So this part here is fine because this is positive, so this is going to be unaffected, it's going to stay the same. But this part here is below the x-axis, so this is now going to have to come on top, so it's reflected like this. Here, these kind of quite unusual, very sharp kind of turns like this. And then this here is on top of the x-axis, so this is unaffected, and this just stays the same as well. So this is the only effect that does this middle part here, and the y-intercept was -8, but it's no longer -8, but it's just the modulus, it's just going to become the modulus of -8. So this is going to become 8, and this is the graph y is equal to the modulus of f of x. So this is the only effect it has, it just makes all the points positive like this. For a cubic, so this part here is below the x-axis, so this is going to come on top of the x-axis like this, here. This here is fine because it's on top of the x-axis, so this is going to stay the same. This here is below, so this is going to be reflected like this. And then this here is fine because it's on top of the x-axis, so this is going to stay the same and be unaffected. And this is the graph y is equal to the modulus of f of x, and all the roots and the y-intercept stay the same. And then for the final example, e to the power of x is e to the power of x minus 2. So this part here is fine because this is on top of the x-axis like this, but this here is below the x-axis, so it's going to be reflected, and it's going to look like this here. The asymptote is also reflected in the exact same way. It's going to become the modulus of -2, so the asymptote is just going to become the modulus of -2, which is equal to 2, and then the y-intercept is the same, the -1 just comes up here to become 1. And then that's the final answer. Now, I know the asymptote actually touches here, but that doesn't really matter. We're just trying to say that the asymptote is to this kind of point here. If we have the function f of x, if we apply the transformation f of the modulus of x, this will reflect the x is bigger than 0 segment. So this will be this segment here. This will reflect this in the y-axis. So this will be reflected on to this side in the y-axis. And what you actually find is you just copy this side on to this side. So for this example, this is 3x plus 5. So this side will remain the same. And then we just reflect this in the y-axis, basically just copy it onto this side. So this is just going to be like this. And then that's just the final answer, where this is y is equal to f of the modulus of x. So we just copy this onto this side. And if you think about it, this makes sense, because this here is 1, 2, 3, 4, 5 for the x values, and then this is -1, -2, -3 for the x values. And we do y is equal to f of the modulus of x. So we basically take the modulus of all of these. So these are just going to become positive. So this is just going to become 1, 2, 3, 4, 5. So therefore these two sides are just going to be the exact same thing. So we're basically just copying this onto this because these are the exact same sides basically. And this is basically just how it works. Here's another example. We have this quadratic here, so this is going to remain the same. And then we just reflect this in the y-axis, so this is going to be like this here, where this is y is equal to f of the modulus of x. This here is 2, so therefore this root is just going to be this reflected, so this is going to be minus 2. For this here, this is going to be the exact same thing. This is unaffected. And then we just reflect this and copy this onto here. So this is going to be this as well. So these two are the exact same thing. And therefore this here, as this is 3, this is going to be minus 3. And this is the graph y is equal to f of the modulus of x. And therefore the final example, this here is going to remain the same. And then this is going to reflect onto this side. So this is going to be like this. This here is the natural log of 2, so therefore this root here is going to be the minus the natural log of 2, and then this is the graph y is equal to f of the modulus of x. So again, this just simply works because basically both these sides basically just become the same thing. So you're basically just copying one side, you're basically just copy and pasting one side onto the other. So I just really quick want to talk about multiple transformations. So I've already made a video slightly dedicated to this in chapter 4 in year 1, so I'm not going to cover it here in depth except in the context of modulus transformations. I've also talked about this in other videos as well, multiple transformations. But at A level you could be asked to do multiple transformations. There's a bit dedicated to this in the book in this section, chapter 2. I'll go for a more exam style question in a sec, but quickly, due to the fact that we can do multiple transformations, a function containing a modulus can lie below the x-axis. So if we have something like this where we have f of x is equal to 2x plus 2, if we apply the transformation y is equal to the modulus of f of x, it will look like this, where we have the y-intercept as 2 and the root as minus 1. If we apply the transformation, the modulus of f of x minus 3, this will shift everything down by 3 to the point where it will look like this, where this part here now actually lies below the x-axis. So this here, this root will be the case when this y is equal to the modulus of f of x minus 3 is equal to 0. So this is going to be, as f of x is this is going to be when the modulus of 2x plus 2 minus 3 is equal to 0, and then we can move the 3 onto the other side to get the modulus of 2x plus 2 is equal to 3, and then we consider when this expression is positive and negative. So when it's positive, it's 2x plus 2 is equal to 3, so this is 2x is equal to 1, so x is equal to a half, so this is this part here, this is a half, and then the other one is going to be when this expression is negative, so it's going to be minus 2x plus 2 is equal to 3, so it's going to be minus 2x minus 2 is equal to 3. Move the minus 2 onto the other side to get minus 2x is equal to 5, so therefore x is equal to minus 5 over 2. So this is this root here, minus 5 over 2. And this y-intercept is going to be, as we're doing, minus 3 compared to up here, and this is 2, therefore this is going to be minus 1. But the main thing to take away from this is because of this multiple transformation here, a part of a function containing a modulus can lie below the x-axis. And then to a more extreme, if we do the transformation minus the modulus of f of x, remember that the minus outside the function here means we'll reflect everything in the y-axis. If we do this, it will reflect everything in the y-axis to the point where it will look like this, where now the whole graph, the whole modulus is below the x-axis like this, where this is the graph of y is equal to minus the modulus of f of x, where this here, because this is 2, this will now become minus 2 because it's reflected in the y-axis. So just be aware of these transformations, as they can make the graph look maybe not what you're expecting with the modulus, as it can come under the x-axis. So here's an example of a question involving multiple transformations and also a modulus. So for part A, we just need to sketch the graph of f of x. It's quite common for multiple transformation questions to ask you this, because then you can base your other sketches around f of x. And this is just reciprocal graphs, so we know how to do this. So if we know this reciprocal graph, it comes down from y like this, and then comes down to x here, then the other side comes from here down like this. And we need to also label the asymptotes, and the asymptotes are at y is equal to 0 here, and the other one is at x is equal to 0 on the y-axis like this here. And then that's the final answer, where these are the two asymptotes and this is the graph y is equal to f of x. So for part B, we need to sketch the graph of minus f of x minus 2. So if you remember how multiple transformations work, the order in which we do the transformations is whatever affects x first. So this is inside the function, so we do this first and then we do the reflection second. So firstly, we do f of x minus 2, which is a translation inside the function, so it's going to shift everything to the right by 2. So it's going to look something like this here, like that, where the asymptote here is also shifted to the right by 2. So this is no longer x is equal to 0, this is now x is equal to 2, and then this graph here is also going to be shifted to the right by 2. So this is going to look like this here, like this, where this is the graph of f of x minus 2. And then this y-intercept here is going to be, so it's x minus 2, so all of the values of x are replaced by x minus 2, so it's going to be 1 over x minus 2. So this is the y-intercept, so this is when x is equal to 0, so it's going to be 1 over minus 2, which is equal to minus a half. So the y-intercept is at minus a half. And then this is the final answer, where this asymptote here is unchanged. This is still where y is equal to 0. And then we need to do the outside of the function reflection, so this is going to be minus f of x minus 2, and this is going to be the function minus x minus 2 under 1, and it's an outside the function reflection, so this reflects everything in the x-axis. So this is going to be reflected in the x-axis like this here, and then this is going to be reflected in the x-axis like this as well. So this is now going to be half y-intercept, because this was a minus a half and just reflected in the x-axis, so this is going to be a half, and the asymptotes is going to stay the same. This is still going to be the asymptote x is equal to 2, and this is still going to be the asymptote y is equal to 0. So x is equal to 2 and y is equal to 0. And then this is the final answer for the final sketch. This is the graph of y is equal to minus f of x minus 2, and it looks like this. So for part C, we need to do this transformation here. So firstly, we're going to do the inside the function part, and then we're going to do the modulus outside the function part. So the first thing we're going to do is f of minus x. So this is an inside the function reflection, so it's going to reflect everything in the y-axis. So this is going to be reflected in the y-axis like this, and then this is going to be reflected in the y-axis like this here, where this is the graph of f of minus x and all the asymptotes stay the same. And then we need to do the outside of the function modulus, so the modulus of f of minus x. And remember what the outside of the function modulus does: anything that is on the bottom of the x-axis gets reflected on the top. So this part here is fine, this just remains the same because it's already on top of the x-axis, but this part here gets reflected on top of the x-axis, so this is going to look like this here, like that. And then this is the graph of y is equal to the modulus of f of minus x, where the asymptotes haven't changed throughout. This is still the asymptote y is equal to 0, and this is still the asymptote x is equal to 0. So here's a question on the modulus function, so pause the video, have a go, and I'll go through the answer in about 5 seconds. So for part A, we need to sketch the transform or the graph y is equal to the modulus of f of x. So remember, for this we reflect anything that is below the x-axis on top of the x-axis. So this part here is fine. This here will just remain the same because it's on top of the x-axis, so this will be unaffected. So this is like this, but this part is below the x-axis, so this is going to get mirrored on top of the x-axis, like this, and then this part here is also fine because this is already on top of the x-axis. Now it says we need to show the coordinates of the points P and Q. P is still going to be the same, it's the same y-intercept. This point is going to be the same, except this time the y-coordinate is mirrored. So this is still 6. Q is equal to 6, but this is now going to be positive 1 instead of negative 1. And that's the final answer. This is the graph of y is equal to the modulus of f of x. So for part B, we have 3 transformations we need to do. The minus x, the 2f, and then the plus 3 on the end. And again, we talked about this in the multiple transformations video, but the order that we would do the transformation is when they affect x. So first it's going to be the minus in front of the x, then it's going to be times by 2, and then it's going to be plus 3 on the end. So this is the order of the transformations. So we'll start with the minus x, and this is an inside the function reflection, which will reflect in the y-axis. So this here, it's going to come onto this side, and it's going to be like this, and then this here is going to be reflected onto this side, so it's going to come down like this, and then this is going to come up like this, and then this is the reflection of minus x, so this is f of minus x. P will still be the same as it's still 0, 11, and this is mirrored onto this side, so the minus 1 is still the same, as it's still the same y value, but the 6 will now become minus 6, so it's going to be Q is equal to minus 6 minus 1. So I just thought I should clear some space for this one, because otherwise we're going to be doing 4 sketches on top of each other, so I thought I'd do it one by one. So now we do the stretch of 2 along the y-axis, so everything is going to be multiplied in the y direction by a factor of 2. So this is going to come down further, like this here, and then this is going to come up quicker, like this, and then this is going to come up quicker as well, like this here. This point here is going to become, so it's still going to be minus 6, it's still the x coordinate, but now it's 2 times as big, so this is now going to become Q is equal to minus 6 minus 2, and then the P point here, it was originally 0, 11, but we stretched it 2 times in the y-axis, so this is now going to become P is equal to 0, and then 11 times 2 is 22. So this is the transformation y is equal to 2f of minus x. I currently use a ruler on a drawing tablet, so I thought I'd just neaten it up quickly with a ruler. And now we have to do plus 3, so this is going to shift everything up by 3 on the y-axis. So this was originally minus 2, and minus 2 plus 3 is 1, so this is now going to be on top of the x-axis, and we'll set it somewhere about here. So this is going to become something like this here, like that, and something like this, something like that. The Q is going to become, so this is still going to be minus 6, and then it's going to be minus 2 plus 3, which is equal to 1, and then P is going to become, it's still going to be 0, and then it's going to be 22 plus 3, so it's going to be 25. And then this is the final answer. Y is equal to 2f of minus x plus 3, where P is equal to 0, 25, and Q is equal to minus 6, 1. So for part B, we're told that f of x is equal to a of the modulus of x minus b minus 1, and we need to state the values of a and the values of b, and to do this we have to use this graph and use the fact that we know the values of p and the values of q and sub them in as the x and the y coordinates. So if we start with q here, it's going to be a of, and then x is 6, so it's going to be 6 minus b minus 1, and this is equal to minus 1. Move the minus 1 onto the other side to get a of the modulus of 6 minus b is equal to 0, and then divide both sides by a to get 6 minus b is, or the modulus of 6 minus b is equal to 0. Now we talked about when this expression is positive and when this is negative with solving modulus equations. When it's actually equal to 0, it doesn't matter, it's going to equal the same thing regardless, so we'll just make it positive. 6 minus b is equal to 0, and therefore b is equal to 6, and therefore what we can do is use this point and know the fact that we know b is equal to 6 in order to find a. So this is going to be a of the modulus, and then x here is 0, is going to be 0 minus b, which we now know is going to be 6, so it's going to be 0 minus 6, and then end of modulus minus 1, and this is equal to 11. Move the minus 1 onto the other side to get a of, and then 0 minus 6 is just going to be the modulus of minus 6, and this is going to be equal to 12. The modulus of minus 6 is just going to be 6, so it's going to be 6a is equal to 12, so therefore a is equal to 2. So the value of a is 2, and the value of b is 6.